right, folks. Good afternoon, or good morning, I should say. Um, Today, I want to take a look at some derivatives that people had asked about. And again, you don't need to know this exactly for the exam. However, some people said, hey, it'd be nice to know where we get this. All right, so the first thing I want to take a look at is how to find the derivative of, say, y equals e to the x. Y equals e to the x. All right? Well, to do this, I need to start by remembering an important idea that we talked about when we were doing limits in the previous chapter. That important fact is that the limit as x approaches 0 of the quantity 1 plus x to the 1 over x power, that equals the value of e, right? Now, I can rewrite that if I wanted to as the limit as any amount u approaches 0 of 1 plus u to the 1 over u is equal to is equal to e. Now again, ladies and gentlemen, this value of u, this guy right here, he typically in math is going to represent some other value, some other complicated looking expression in terms of x or some other variable. Okay, so now let's keep this in mind, this rule that we've just been reminded of, and let's take a look at the function y equals e to the x. Suppose I want to find the derivative of this using the definition of the derivative. Well, I know that the definition of the derivative says y prime equals the limit as h approaches 0 of this function, but instead of x, it's f of x plus h, so e to the x plus h, minus the original function, e to the x, over h. And again, don't forget that that's just this slope formula, y2 minus y1 over x2 minus x1, that's been simplified, okay? All right, so now, to do this, to simplify this, I first need to do a little bit of algebra here, okay? Now, the algebra that I'm going to do, well, let's see here. We know that e to the x plus h, well, anytime I have an exponent added, I know that's the same thing as the product of the bases multiplied. So I'm going to rewrite this as y prime equals the limit as h approaches 0 of e to the x times e to the h. Right? Does everyone see how e to the x times e to the h would be e to the x plus h right here? All right, so minus e to the x over h. All right? Well, from there, as you can tell, I have an e to the x in this first term, and I have an e to the x in the second term. So now I'm going to factor out an e to the x. So by doing so, I'm going to get e to the x, parentheses, e to the h, and then minus 1 all over h. All right, now let's focus in on this e to the h term right here, right? Watch a little bit of magic that I'm going to do using some algebra. I'm going to come back up to this idea right here. I know that, in general, the limit as x approaches 0 of 1 plus x to the 1 over x power is e. Well, that must mean that I could say that 1 plus h to the 1 over h power would have to equal e as the limit of h approaches 0. Agreed? Okay. Well, wait a minute. What happens if I take this expression right here and I take the e? Well, isn't it true that what you do to one side, you have to do to the other? And as long as you hold that holds true, I can do whatever I want. So what I'm going to do is I'm going to raise both sides to the power of h. Okay? Well, what that must mean is the limit as h approaches 0 of 1 plus h to the, well, wait a minute, don't you multiply exponents when you raise the power to a power? To the first power, or just 1 plus h, has to equal e to the h power, as h approaches 0, of course, right? Well, based off of that, here's what we can say. I can replace this e to the h up here with just 1 plus h. All right? By doing so, I get a new equation. Now, hold on tight just for a second. I'm going to erase everything that I've just written. Okay, now, again, I've established that e to the h is equal to 1 plus h using the limit as h approaches 0 as above. Using substitution, I can say then that y prime then has to equal the limit as h approaches 0 of e to the x times, well, again, I'm going to put this in for this e to the h, so I'm just going to get 1 plus h minus 1 over h. Does everyone see how I got that? So therefore, using a little bit of simplification, the limit, the derivative as the limit as h approaches 0 would just be e to the x times, well, doesn't the 1 and the negative 1 cancel, leaving me with h over h? Well, the h's cancel, so the derivative of y prime would equal the limit as h approaches 0 of e to the x. Well, again, wait a minute, I don't have anywhere to plug this h in anymore, right, since the h is canceled, so that must mean that the derivative of this function just must be e to the x. And I've shown you that the derivative of y equals e to the x is equal to itself, e to the x. Okay, let's do it again now with the function y equals the natural log of x. Okay? Again, using the definition, I know that I can say that y prime is equal to the limit as h approaches 0 of the natural log of x plus h minus the natural log of x over h. Correct? Well, based off of my properties of logs, couldn't I take this numerator of the natural log of x plus h minus the natural log of x, and couldn't I condense that into a single log that says y prime equals the limit as h approaches 0 of just the natural log of x plus h over x all over h? Does that make sense? Okay, now from here I can say, well, gosh, that's the same thing as the limit as h approaches 0 of, well, I could separate this argument into two fractions, x over x and h over x. Well, wouldn't that just become the natural log of 1 plus h over x over h? Does everyone see how we got that? Okay, now at this point, I'm going to have to try and get this 1 plus h over x. Golly, that seems like something similar to this definition of e in terms of the limit, right? So here's what I'm going to do. I'm going to do a little bit of substitution. I'm going to let h equal u times x, all right? Well, by doing so, I can create a new expression for the derivative as the limit of the natural log of 1 plus, well, let's see, if I replace h with u times x, wouldn't it become ux over x all over ux? And instead of the limit as h approaches 0, again, I could either do it as the limit as u approaches 0 or of x approaches 0, right? I can only do it for one variable. So I'm going to say I want to find the limit of this expression of this function as u approaches 0 this time. Okay? All right, so as you can see, I've changed the original limit using substitution from as h approaches 0 with h's in it to the u approaches 0 with u's in it. Now I'm going to do some more algebra. I'm going to go the derivative then equals the limit as u approaches 0 of, guys, would you agree that anytime I'm dividing, isn't that the same thing as multiplying by the reciprocal? So could I rewrite this as 1 times u over x times the natural log of 1 plus ux over x? Everybody see that? Well, wait a minute. By taking this 1 over ux and bringing it out in front of the natural log and making it a coefficient of the natural log, we know the properties of logs. Anytime I see this exponent, this coefficient, couldn't I bring it up and make it the exponent of my argument? So couldn't I rewrite this as the derivative is equal to the limit as u approaches 0 of the natural log of 1 plus ux over x to the power of 1 over u times x. Everybody see that? All right, again, doing some more simplifying now. I'm going to get the derivative is equal to the limit as u approaches 0 of, well, inside of here, couldn't I just create this ux over x? Isn't that just 1 plus u? Oh, I'm getting somewhere. These cancel, right? So I'm just left with 1 plus u to the power of, well, again, couldn't I split this exponent up into two things multiplying? Couldn't that be to the power of 1 over u times 1 over x, right? Doesn't that make sense? 1 over ux is equal to 1 over u times 1 over x. Well, wait a minute. That's the same thing as y prime equals the limit as u approaches 0 of the natural log of, and instead of u 1 over u times 1 over x, I'm going to write it as 1 plus u to the 1 over u to the 1 over x power. Isn't that true? Right? Well, wait a minute. Because I've got the natural log of this argument here inside the brackets raised to the power of 1 over x, couldn't I take this power and bring it down here to the front? And wouldn't that become the derivative is equal to the limit as u approaches 0 of 1 over x times the natural log of 1 plus u to the 1 over u power? Now again, because I'm taking the limit with respect to the variable u, this 1 over x factor, he can actually come out and just become y prime equals 1 over x times the limit as u approaches 0 of the natural log of 1 plus u to the 1 over u power. Oh my, jinkies, look at this. If you look at this, didn't we say our original supposition that the limit as u approaches 0 of 1 plus u to the 1 over u is e? Well, because of that, I can say that the limit as u approaches 0 of ln of 1 plus u to the 1 over u power, well, again, guys, I know that this is e, so isn't this just the ln of e? So I'm left with y prime equals 1 over x times the ln of e. But guys, what is the natural log of e? Isn't this just 1, right? So the derivative is just 1 over x times 1. So the derivative of the natural log of x is just 1 over x, right? But hey, now that we've talked about implicit differentiation, let me show you another technique for finding the derivative for y equals the natural log of x. Let me erase all this rigmarole that I did for the definition, and I'll be right back. Okay, let me show you another way of doing this. Suppose I have y equals the natural log of x, and I want to find the derivative of this function, all right? But would you agree that this equation is in explicit form in terms of x? So watch what I'm going to do here. I'm going to rewrite this function instead of in logarithmic form, in exponential form. If I did that, wouldn't this function become, well, let's see here. I'm going to actually, before I do that, I'm going to go y equals, doesn't this mean log base e of x? And we know that to change from log to exponential form, the base of my log, which is e, will become the base of my exponent. And it'll be e to the y equals x, correct? Okay, now, if I want to take the derivative of this new function that's written in exponential form, as you can see, my variable y is not alone. So this would be an implicit equation. So to take the derivative of this, don't I have to take the derivative implicitly? So to do that, let's see here. I would first take the derivative of the left side, so the derivative of e to the y in terms of x, and the derivative of the right side, the derivative of x in terms of x. Well, again, the derivative of e to the y is just e to the y times y prime. You guys said you like y prime better. And that equals the derivative of x in terms of x is just 1, right? Okay, well, if I solve for y prime, don't I get y prime equals 1 over e to the y? Right? Now, wait a minute. This variable y, I know what y equals. Doesn't y equal ln of x? So couldn't I replace this y with 1 over e to the ln of x? Agreed? Well, wait a minute. Do you recall from our days in algebra, anytime the base of my exponent and the base of my log, which is e, if those match, don't those cancel, giving me just the argument? So wouldn't my derivative just become y prime equals 1 over x? Again, over here on the side, I'm going to give you an example of what I'm talking about with this e to the ln of x. Suppose I have something else. Suppose I have 5 to the log base 5 of, say, x, right? And I want to know what this simplifies to. Well, this is some type of exponential equation. Would you agree? Well, let's take a look at this. If I wanted to set this equal to some other variable, call it y, and I'm going to rewrite this in now log form, wouldn't I get, well, let's see, this is the base of my exponential, so log base 5 of, well, if this becomes the base of my log, doesn't my exponent become the answer and the y becomes my argument? So doesn't it say log base 5 of y has to equal the log base 5 of x, right? Well, because of that, doesn't that say then the log of 5s are not necessary, and I can just say the arguments must be equal, so y must be x. In other words, again, if I see this, I know that the value of this is just x, right? Y must equal x, as I've just proven here, right? Well, similarly, that's what I've done here. Okay? I've said that since I've got e to the ln of x, since these bases match, the answer to this expression must just simply be x. So I've just proven the derivative is 1 over x, but instead of using the definition of the derivative, I've used implicit differentiation. Okay? Hope that makes sense. Later on, I'll show you again, actually at the end of implicit differentiation, how we can do the same thing with y equals e to the x. Okay? Let's do one more involving e. Remember how I just said that e to the sorry. Remember how I just said that e to the ln of any argument a is just a, right? Well, look how you can use that little piece of information as a tool to help me find the derivative of y equals a to the x. Okay, where a again can be any base greater than 0, but not 1. Well, let's see, if I want to take the derivative of this guy, right? Well, watch what I'm going to do here. Instead of using the definition, I'm going to rewrite this equation as this. Would you agree that this would be the same thing as e to the ln of a to the x power? Agreed? Right? Again, we just said that if I have e to the ln, don't those cancel, giving me just my argument as my final overall answer to that? So we know this is true, right? So now, because I know how to take the derivative of e, not a, but e, I can say, oh, well, the derivative of this would be y prime equals, well, the derivative of this e expression is just that expression, e to the ln of a to the x, right? Now, I have to now take the derivative of the second part. I have to take the derivative of ln of a to the x. Well, again, before I do that, I'm going to rewrite the ln of a to the x. Isn't that the same thing as x times the ln of a, right? Well, if I want to find the derivative of x times ln of a, wouldn't the derivative of x just be 1? And the ln of a is my answer, right? So the derivative of this function would be the derivative of the outer function, e to the ln of a to the x, which is just e to the ln of a to the x, times the derivative of the inner function, which is this exponent, which just becomes ln of a, right? Well, wait a minute. Now that I've done this, couldn't I take this expression and couldn't I rewrite it back as it was originally? Didn't we say that e to the ln of a, that cancels? Wouldn't that just be a to the x again? Times the natural log of a, right? So I know that the derivative of a to the x is just the natural log of my base times a to the x. And that's where that comes from. Let's take a look at doing some trig derivatives now. Let's take a look at the y equals cosine of x, right? Suppose I want to find the derivative of this function. Well, again, I'm going to go back to the definition and say that the derivative is equal to the limit as h approaches 0 of the cosine of quantity x plus h minus the original function cosine of x over h, right? And again, that's just your slope formula. Now, this guy right here, the cosine of x plus h. Well, back in pre-calc, you learned something called the sum and difference formulas for sine, cosine, and tangent, all right? Well, here's a great application of that. As you recall, you learned that the cosine of any two angles added together, call them u plus v, is equal to the cosine, I'm going to come down here, the cosine of u times the cosine of v minus the sine of u times the sine of v, right? Well, in this case, instead of u's and v's, I've got x's and h's. So, we can say that the derivative will be the limit as h approaches 0 of, expanding this, wouldn't it be the cosine of x times the cosine of h minus the cosine of x, minus the sine of x times the sine of h minus this cosine of x, and that's all over h, right? Now I'm going to do some manipulation of this expression. I'm going to take this cosine of x right here, and I'm going to bring it closer to this cosine of x over here. By doing so, I get the equation, or the derivative, equaling the limit as h approaches 0 of the cosine of x times the cosine of h minus the cosine of x minus the sine of x times the sine of h, and that's all over h, right? Now, the next thing, I know that as fractions work, since every term is being divided by h, I can split this up into 3 fractions if I wanted to, correct? I can also split it up into 2 fractions. I'm going to split this up into this fraction right here. I'm going to take these 2 first terms, I'm going to make those the numerator over h, and then I'm going to take this last term right here, and I'll put him over h as well. Okay? By doing that, I get an equation that looks a little like this. The derivative will equal the limit as h approaches 0 of the cosine of x times the cosine of h minus the cosine of x over h minus the sine of x times the sine of h all over h. All right? Now, by doing so, would you agree that I can factor out a cosine of x from these first 2 terms in this first fraction? I would get the derivative is equal to the limit as h approaches 0 of the cosine of x times the quantity cosine of h minus 1 all over h minus the sine of x times the sine of h all over h. All right, now, if you go back to our squeeze theorem limits, this one right here, the cosine of h minus 1 over h, this should look familiar. As a side note, recall that we figured out that the limit as any variable, in this case h, of 1 minus the cosine of h over h, well, that always approaches 0. So we know that the limit of that is 0, right? Similarly, don't let us forget that the limit as any variable, such as h approaching 0, of the sine of h, the sine of h over h. Well, by the squeeze theorem, we know that approaches 1, right? Well, watch how I can do this then. Again, we're taking the limit of this function in terms of as h approaches 0, correct? So going back into our function after that little stroll down memory lane, couldn't I rewrite this as the derivative of y is equal to the cosine of x, because again, I'm not taking the limit with x, I'm taking it with respect to h approaching 0, of the limit of the cosine of h minus 1 over h minus the sine of x of the limit as h approaches 0 of sine of h over h. I don't know why these little boxes are appearing. I apologize for that. Okay, I'm a bad boy here. That should be approaching 0. H approaches 0, right? Well, again, guys, if 1 minus cosine of h over h is equal to 0, does it matter that cosine of h minus 1 is over h? Does it matter that the signs have switched places here? Wouldn't that just be negative 1 of this item right here? But negative 1 times 0 is 0. So this still is going to approach 0. Okay? So the derivative would equal just the cosine of x times 0 minus the sine of x times, well, wait, what's the limit as h approaches 0 of sine of h over h? Isn't that just 1? So wouldn't it be the sine of x times 1? Well, simplifying the two terms, I would get the derivative equals, well, cosine of x times 0 is just 0, and then negative sine of x times 1 is just negative sine of x. And I've just proven to you that the derivative of cosine of x is negative sine of x. Yeah? Who knows, maybe on a bonus, as a bonus question, I might ask you to find the derivative of sine of x using the formal definition as an extra credit. So if you watch this, maybe that'll be helpful. All right, guys, let's see. Is there anything else I'd like to talk about? Oh, I remember Lewis asked me a question that talked about just notation. I remember telling you that for higher order derivatives, such as the second derivative and the third derivative and so on, there's a funky notation. We said that, all right, if I'm given the original function f of x, right, well, that's the same thing as y. And we said the derivative of that would be f prime of x, right, which would be the same thing as y prime, or dy dx. Those are the three popular notations for the derivative, correct? Right? Well, take a look at this. If I wanted the second derivative, that would be the second derivative of x, or y, or d2 y over dx2, right? Well, here's just a real brief explanation of this, right? Again, suppose I have some function, y, equaling some function over here, f of x, right? And again, I really don't care about the right side. I'm just going to explain why the notation. Well, to take the derivative of this function, I say the derivative with respect to y of this guy with respect to x is equal to the derivative of f prime of f of x, which would be just this, right? Well, what if I wanted to take the second derivative of this? Well, again, wouldn't I take the derivative of this guy? So wouldn't this be the derivative of this function with respect to x times the derivative of f prime of x would just be another prime, right? Well, again, and this isn't really what's going on. These aren't really operators such as squaring or whatnot. But do you see how I've got in here two d's, a d and a d? They're not multiplying, but do you see how I've got a pair of d's here? Well, doesn't that look like d squared of y? Whereas on the bottom, don't I have a dx, what looks like times a dx? It's not dx times dx, but it looks like that, correct? Right? Well, that looks like I'm squaring the dx, right? So you'll often see the second derivative written as d2y over dx squared. And again, I've got a pair of d's, hence the d squared. I've got two dx's, hence the dx squared. And that's the notation that we use, and that's the reason. I mean, again, could I go further, a further extension of that, and say, well, gosh, if I took the derivative of this, making the third derivative, if I did another one, does it make sense why that would be now, well, a d and another d, two d's would become 3d's with respect to y and dx cubed, right? And so that's the notation that we use. Okay, even though again this is not multiplication. All right, folks, and that's the exponentials of that. Let me know if there's anything else you want to talk about. Talk later. Bye.